Pancreatic cancer is one of the deadliest malignancies because it often develops without triggering physical symptoms. By the time a patient presents with symptoms, the disease has usually advanced to a stage where surgical removal is no longer possible. Clinical records show that the biological precursors to this cancer are often captured on routine CT scans years before an official diagnosis. These early signs are missed because they exist below the threshold of human visual perception, appearing as healthy tissue to even the most experienced radiologist. Shifting survival odds requires a method of detection that operates beyond the physical capacity of the human eye. In April 2026, researchers at the Mayo Clinic published a validation study in the journal Gut detailing a new approach to this visual limitation. Their research centers on an AI model called REDMOD, or the Radiomics-based Early Detection Model. REDMOD moves away from human visual analysis of macrostructures, using computational feature extraction to analyze the pancreas. This method allows the model to identify signatures of pancreatic cancer on routine scans, up to 3 years before a clinical diagnosis would otherwise be made. The algorithm calculates the mathematical probability of a tumor's arrival by identifying subvisual signatures within the tissue. Implementing a new population-wide screening program for a specific cancer requires massive logistical coordination and financial investment. REDMOD circumvents these barriers through a strategy called opportunistic screening. This means the model does not require a new type of imaging or a dedicated diagnostic appointment. Instead, the algorithm piggybacks on routine abdominal CT scans already being performed for unrelated conditions, such as kidney stones or appendicitis. The model automatically isolates the pancreatic region from these general abdominal scans to begin its targeted analysis. Hospital archives already contain the necessary diagnostic data. The development of REDMOD provides the method to extract it. Standard radiology relies on specialists looking for visible, macrostructural anomalies like tumors or cysts. Radiomics treats medical images as high-dimensional quantitative data arrays. Every CT scan is composed of voxels, 3-dimensional pixels. Each voxel is assigned a Hounsfield unit, a numerical value representing the density of the tissue at that point. REDMOD transforms these voxel values into hundreds of mathematical matrices for analysis. This data is then categorized into 2 primary layers, structure and texture. The texture layer measures the spatial distribution and subtle heterogeneities of the tissue at a cellular level. These microheterogeneities are the faint biological changes that occur as a cancer begins its earliest development. These mathematical deviations precede the formation of any physical mass visible to the human eye. Decoding tissue texture allows for the observation of the environment that breeds cancer before the cancer itself has fully formed. To validate the model, researchers used it to analyze nearly 2,000 CT scans from multiple medical institutions. This data shows that REDMOD identified 73% of cancers in scans taken before a clinical diagnosis was made. This detection rate is nearly double that of specialist radiologists reviewing those same images. The difference is even more pronounced when looking at scans taken more than 2 years before diagnosis. In this early window, REDMOD caught nearly 3 times as many cancers as the specialists. While human specialists are limited by biological optics, computational analysis can identify patterns in the underlying raw data. These results indicate that REDMOD can extend the lead time for medical intervention from months to years. Validating an algorithm on past data is a vital proof of concept, but the final hurdle is deploying it for live patients. Mayo Clinic researchers are currently running a prospective clinical study called AI PASTE to test this transition. AI PASTE evaluates the methods for integrating REDMOD's predictive flags directly into a physician's active workflow. This trial focuses on managing care for high-risk patients over a 6-month evaluation period. The results of this study will determine how quickly radiomics becomes a standard part of clinical care. This work represents a transition from reactive diagnosis based on visible structures to predictive mapping based on algorithmic data. Identifying the precursors of cancer before a mass forms provides the highest statistical chance of successful treatment.